So in this video, we're going to look at gravitational potential energy and kinetic energy, and then we'll put the two together to talk about mechanical energy. So first, gravitational potential energy. That's the energy of an object that has mass that's been lifted some height above a surface. So it's also, you can talk about gravitational potential energy out in space, but we're going to focus just on objects near the surface of the Earth because that's where we spend most of our time. So the gravitational potential energy of an object near the Earth's surface depends on the object's mass. So if you think about it, if you lift a large boulder above the surface of the Earth, or you lift a small pebble above the surface of the Earth, above the ground, which would be you'd be more nervous about dropping, right? It'd be the large boulder would make a bigger impact if it dropped. You'd be more worried about that one. And that's because it has more gravitational potential energy, because it has more mass. The other thing that impacts gravitational potential energy is the acceleration due to gravity, so g, at the location of the object. So that's going to be 9.8 meters per second squared for us on the surface of the Earth, but that'll depend on which planet you're on too. The last thing that gravitational potential energy depends on is the height of the object above usually the ground or any sort of defined 0 point. So we can actually pick the sort of 0 height to be anywhere, and then we measure gravitational potential energy up from that. The ground just usually makes sense. And that kind of fits with our intuition too, right? If you have a heavy object and you've lifted it 10 meters above the ground, or you just lift it like half a meter above the ground, you're going to be nervous about dropping an object that's 10 meters above the ground, more nervous about that than dropping an object that's only half a meter above the ground, right? So the height impacts the gravitational potential energy as well. Our symbol for gravitational potential energy is E for energy and subscript G for gravitational potential energy. By the way, another symbol is capital U. We won't use that in our course, just to be consistent. We're going to have all of our energies be capital E's and then a subscript, but just so you know that's out there. The SI units are joules, so J for joules. Now, to actually derive the equation for gravitational potential energy, we're going to use work. And we're going to use the work done to raise an object mass m, some height h. So our y1 will be 0, it'll be on the ground initially, and we're going to get up to a y2 of h. We're going to assume we raise it at constant speed, so then our free body diagram will look like this. We'll make our coordinate system up is positive, there'll be an applied force, Fa, there'll be a gravitational force, Fg here, and those forces should balance out. So my net force in the y direction will be applied plus gravity, and that net force in the y direction will be 0 because we're going to assume constant speed here. Or in other words, the acceleration in the y direction is 0. So that means 0 will equal Fa plus Fg, and let's fill in what those are. So Fg is negative mg. That lets me solve for Fa, right? I move the negative mg to the other side, it becomes positive, and I get Fa is equal to positive mg. All right, so that's the force you would have to apply to lift that mass at constant speed. What I want to know is what's the work done to raise that mass a height of h. So work is F dotted with displacement. So here, the force is straight up, and the displacement is also straight up. So those are parallel to each other, so my dot product here can just become multiplication. That means the work is going to be just the Fa multiplied by h. Or I'll plug in what Fa is, mgh. Work is basically a way to talk about transferring energy. So the work done on this mass to lift it from 0 up to h is actually the energy that we give it. So the energy that it has once we've lifted it up is mgh. That means if it started with no energy when it was on the ground and now it's gained this much energy, its gravitational potential energy is mgh, which is actually the equation for gravitational potential energy. So our gravitational potential energy equation is Eg equals mgh. M is the mass of your object. G is 9.8 meters per second squared. Notice that's just a constant, 9.8 meters per second squared. It is not negative. When we've talked about negative G, that came from the sign of a free body diagram. There's no free body diagram in this at all. This is just a number G. H is how high you've lifted it above the ground, or whatever 0 is in your problem. All right, let's do an example. So let's say you have a 50 kilogram student who is standing on their chair. They have a mass, their center of mass is 1.1 meters above her feet. She's standing on her chair, which is also 0.6 meters above the ground. So that means her height above the ground is going to be the 1.10 meters plus another 0.6 meters, or in other words, her height will be 1.7 meters above the ground. I know her mass is 50.0 kilograms, and I know the constant g is 9.8 or 9.81 meters per second squared. I'll use the 9.81 just to be a little more precise. Her gravitational potential energy then is mgh. We know all of those things and it's already nicely rearranged. So I can just put in my numbers, 50, 9.81, 1.7. Toss that into your calculator, 50 times 9.81 times 1.7. And we get 833.85. I have three significant figures here, so I'm going to round off to Eg is 834 joules. Oh, by the way, this is one of those tricky sig fig rules. Looks like I only have 2 sig figs here, but when I got my final height, I did it by adding and adding. You keep the decimals, and then my final height had 3 sig figs. Just a little bit of a sneaky adding sig figs rule. We don't often do the adding rule for significant figures, but we do have adding going on here. So that's a short aside. Kinetic energy. That's another really important type of energy that we'll be using in this unit. So kinetic energy of an object is all about the energy of a moving object. So it depends on 2 things. It depends on the object's velocity. So that kind of makes sense. You have more kinetic energy if you're moving faster. It also depends on the object's mass. Right, so you would be more nervous about a baseball that's thrown really fast than one that's thrown slow, so velocity matters, but you also care about the mass. Like you'd be more nervous about a giant boulder thrown really fast than a baseball thrown really fast. So the mass matters too. The symbol for kinetic energy is EK. Just as an aside, you might see just K as kinetic energy in some places, but we're going to use E for energy, K for the subscript of what type of energy it is. The SI units are joules, so J for joules. And the equation for kinetic energy, so EK, is 1/2 times the mass times the velocity squared. Cool, so 1/2 mv squared. We'll do a little problem with that. So let's say you have a baseball, it has a mass of 150 grams, a velocity of 34.5 meters per second. We want to know its kinetic energy. So what do I know? My mass is 150 grams. Notice that's not an SI unit, so I need to convert that into kilograms. So that's going to be 0.150 kilograms. And I have a velocity is 34.5 meters per second. My kinetic energy is 1/2 mv squared. So I get to plug in my numbers. 1/2 times 0.15 times the 34.5 squared, and toss it into your calculator. I like to do this part first. So I do my squared first, and then times the 0.15, and then times the 1/2, and I get 89. In this case I have 3 sig figs, right? So it'll be 89.3 joules. So 89.3 joules is my kinetic energy. All right, one last type of energy, which is actually not a new one. This is actually just the combination of kinetic and gravitational potential energy. So mechanical energy, its symbol is m.E for mechanical energy, and it just equals the gravitational potential energy, Eg, plus the kinetic energy, so EK. And that forms what's called the mechanical energy, which for some objects is actually its total energy. For a lot of the objects we'll be using in this unit, that is going to be its total energy. It's gravitational plus its kinetic. In grade 12, you're going to start adding more different types of energy, and you'll see that total energy is a lot more than just these two. But for our first introduction to energy here, we're going to keep it a little more straightforward. Our mechanical energy will often be the total energy of an object. So I could expand this, right? So if mechanical energy is gravitational plus kinetic energy, then I could replace this with the equation for gravitational energy. That's mgh. And I could replace this with the equation for kinetic energy, which is 1/2 mv squared. And that gives me my total equation for mechanical energy all expanded out. And that's it.